Greg. So why did we think it was important to give a presentation on our filling and weighing technologies? As products and technologies have become more advanced, the need for accurate and hygienic filling of materials has become ever more important. With a range of requirements from customers being so broad, we thought it would be a good opportunity to show how our solutions can be used to satisfy current and future needs in the marketplace. We would like to show you that Hosokawa has for decades been one of the original suppliers of packing heads, and also explain how and why our systems work, and also give some examples of installed plants along the way. Why containment? Is it to protect the product from contamination, or protect the operator from the product? Of course it's the latter one usually, protecting the operator. It can be to maintain the area classification in which the system is located, protect the local environment. But as we just touched on, operator protection is the main consideration on a majority of applications. Increasing legislation, for example from the US and Europe, means more stringent measures need to be put in place to comply. Of high importance on a lot of our applications over the years were the explosion protection measures, which means equipment being suitably rated for such zones, and in the last 10 to 15 years especially, the introduction of ATEX in Europe or under the similar NAFTA measures in the USA. This has meant the need for increasing containment, as failure to do so can lead to bad housekeeping and even explosions in the workplace. Operator exposure levels or operator exposure bands. Company health and safety will assign products to one of these levels or bands depending on their potency and effect. It is worth noting at this point that certainly in the pharmaceutical industry, different companies have slightly different OEB bands, and so it is wise to check what the actual band relates to. Traditionally, even up to 5 or 6 years ago, we were being asked to provide systems to milligram containment levels, or typically 100 microgram per meter cubed. Whereas now the shift, certainly with the more potent compounds, is for the OEL levels to typically be in the 10 microgram range or even less than 1 microgram. And here's a guideline matrix showing where Hosokawa's equipment may be used. Particle pollution contains microscopic solid or liquid droplets that are so small they can cause serious health problems. In general, the size of particle is linked directly to their potential for causing such health problems. Under the USHA Act in the US or COSH in Europe, employers are responsible for providing a safe and healthy workplace and must comply with all applicable standards. Let's now look at a very brief history of Hosokawa Micron's filling and weighing technologies. As you can see, LE Stock began in the 1980s and joined the Hosokawa group in the mid-90s along with Vitalair, who manufacture the downflow booths. And as we moved into the next century, you can see there has been some notable achievements. Filling and weighing systems maintain a high level of containment and product integrity, combined with an ease of operation. Very precise dosing can be achieved when used in conjunction with a high accuracy weighing system and appropriate flow control devices. Suitable for use with a variety of products, from sticky foods and pharmaceuticals to fine and free-flowing chemicals and minerals, all our systems are built to customer specifics, including hazardous area and ATEX approved systems. Here we have a diagram of the Hosokawa packing head, complete with a compressed air or nitrogen purging extract sequence and internal filter to reduce product loss to the exhaust system. The 3D drawing shows the filling chute, the purge bars, the IF filter and the packing head itself. For the sequence to commence, a bag must be connected onto the packing head and the extract valve opens for maximum extraction. And the bag liner collapses due to the extraction. An extraction takes place through the IF filter, shown here in yellow. Once the bag is fully collapsed, the purge valve then opens, inflating and shaping the bag. To remind ourselves, we can see the purge bars here that have just inflated the bag, with the IF filter is reverse flushed at this point to clean it, and any powder on the outside of the filter is knocked off via the annulus into the bag about to be filled. You can see here the internal filter, the outer chute having been removed for clarity. At this point the extract valve is slightly open and the unit's ready to fill. A second extract stroke purge sequence can take place if required. Powder dosing now starts as shown by the green, and note that the sequence I've just run through takes place all in a matter of seconds. Displaced air or nitrogen is exhausted through the IF filter either to a safe change filter stack or reverse jet filter, or to a client provided LEV. The inflatable downward sealing head, of course shown upside down in the photograph here, it's used where the head is static and the seal is inflated down onto the rim of the drum. The drum can have a liner in it, or not as required. The head can be inflated upward onto the outlet of, say, a rotating mixer or dryer where the outlet is only static during discharge of the equipment. Typical applications: IBCs, drums, process equipment. And a typical example shown here is the drum on powered roller track with the inflated head down onto the rim of the drum. Downward sealing head solid seal. Because it is a solid seal, it has to travel to seal on the drum or similar, i.e. it has to extend downwards to meet the item being filled. Again, typical applications are similar: IBCs, drums, process equipment. An example of such a system is the IBC liquid filling system, shown here: the solid seal in the bottom, pneumatically operated sealing head, butterfly valve controlling the filling, an extract duct for displaced air. The IBC is inside the horizontal laminar flow booth, with the downward sealer extended down onto the IBC, and the IBC is sat on the pallet, which in turn is sat on a U-shaped weigh scale. Here's another example of an IBC inside a horizontal laminar flow booth, with the downward sealer shown here inside the booth, again extended down onto the actual IBC. Outward inflatable sealing head. This has been proven technology over many years, pneumatically operated with compressed air or nitrogen if required. Used mainly nowadays for single liners, but can be used with continuous liner as well. Examples of the outward inflatable sealing head is shown here. There's a deflated seal, a liner loading cage, there's a double purge valve in series, which some clients prefer, an extract valve, exhaust line, there's a sampler, pneumatically operated, with collection jar, and there's the local exhaust vent. A second example of an outward sealing head is this particular one, the outward seal inflated, continuous liner, there's a heat sealer, roller track, all back mounted onto the weigh scale to provide accurate weighing. And here's a couple more examples, complete with the Hosokawa pinch valve, controlling the flow of material into either unit. The compact inward inflatable seal. The great advantage of this is that the seal does not come into contact with the product. Most compact seals can be raised, lowered manually on gas struts or pneumatic cylinder. Shown here is a version where the sealing head is swung up into the position, or down to the side, out of the way. The beauty of this system is that it can be retrofitted onto almost any existing installation, and typical examples tend to be in the pharma, food or high-end chemical. The seal is pneumatically operated and is seen here in blue, most suitable for hazardous areas as it is highly sanitary and GMP with FDA approved seal materials. Two examples of the compact inward sealer. The left photo shows a pneumatically operated inward sealer with single liner, where the cylinders for operating the head are installed on the filling head itself. The right photograph shows an inward sealer, again in the lowered position, pneumatically operated, again back weighted onto the weigh scale with a roller track to aid drum transfer. Single and continuous liner systems. In the left-hand photo is a packing head capable of being used with a continuous liner. Note that the liner loading cage is fitted, but in this instance is being used with a single blue liner. In the right-hand photo is a continuous liner system complete with pre-packed liner, having just been changed. This slide shows the continuous liner system and how it works. This is the liner loading cage, complete with liner loaded onto it, the outward sealing head. One end of the liner is actually held by O-rings and the other end is actually tied complete. This liner is then pulled down into the drum to be filled. Product is charged through the filling head, and then the filled liner is net, tie-tied and cut in between to form a seal. You then have the liner in the drum with filled product and the tied liner fully sealed, ready to accept the next drum and lot of product. Some examples of continuous liner systems. Left-hand photo shows an older style inward sealing head with continuous liner. The right-hand system shows what we call the shower cap, left on the filling head sealed by the O-ring and tied below, this being the O-ring. The head of course here is operated by pneumatic cylinders. The liner loading table is the cheapest way of using liner in the filling process. The amount of liner you can get on a cage is liner thickness dependent. This leads to the number of drums you can fill before having to change the liner loading cage to continue the operation. The alternative is pre-packed liner, which comes packaged ready for installation, either onto a liner cage as normal, or there are versions that can be used pre-loaded, some onto a cardboard support, which replaces the traditional metal liner loading cage, but these are very expensive compared to the liner rolling table. To crimp the liner, you squeeze the two clips together around the liner using the crimping tool, and then you can cut between the actual clip, which then produces the two parts of the liner. This particular type of clip then comes with a cap on both ends, so both can be sealed. An alternative system is the Clasp System, essentially a large double cable tie system tightened with a manually operated ratchet gun. Again, you cut between the tie and reveals a solid clasp of plastic liner. There is a pneumatic gun option available for this system. The horizontal laminar flow booth is to provide secondary containment to the packing head itself. It works by air being sucked into the front of the booth, providing a nominal ½ meter-second airflow over the front face. Any airborne particulate is taken to the rear of the booth, away from the operator, and extracted to the associated filter fan unit or client LEV. The unit typically has a top screen to provide protection to the operator's breathing zone. The unit can also have lower doors or even full doors. Here's a typical unit with upper screen. This unit also has a top screen. back-weighted frame onto the weigh scale complete with roller track, vibratory table shown here straddling the weigh scale, and this system is typical for a chemical application. To go with the horizontal laminar flow booth is a safe change filter unit, either a 2-filter unit, can either be a fine filter followed by a HEPA or 2 HEPAs. This is for smaller booths, and as the booth size goes up, so the air volume goes up accordingly, and as can be seen on the right hand side, this unit supports a much larger horizontal laminar flow booth. This shows ideally the integration of the 3 items, the horizontal laminar flow booth, the filter, and the fan set. Another secondary type of containment glove box, which in essence becomes the primary system, is the glove box pack-off system. The fill-way system, shown here, is installed in the glove box. The drum to be filled is connected to the bottom of the glove box here. The benefits of this system is that you can achieve very low OELs, and it's totally sealed from the operator. Some limitations is that the unit is expensive, and there can also be limited space in the chamber itself. Here's another example for highly potent pharmaceutical products. And again, this is a pack-off, shown here, with an additional drum chamber on the left-hand side to clean the drum before exit. Pack-off systems can also go inside a downflow booth. 0.5 meters a second airflow is coming down from the ceiling, taken away to the back of the booth, where it's filtered through 3-stage filtration. The downflow booth itself can be recirculation type or a single pass type. The powder train above the fill-way system is key to providing accurate filling and weighing of the product. The design of the system does depend on the nature of the product. Here we have the Hosokawa Stott designed pinch valve. Dating back to the earlier days of Stott, it has a rubber sleeve which forms the last part of the internals of the filling chute, and a knife plate operated by a pneumatic cylinder that pinches the rubber sleeve closed. We can show here the video. It shows the pinch valve operation, the packing head inflated, the pinch open to bulk fill the product, bulk filling commences, the pinch is closed to set point 1 and then open to dribble fill, and at the same time the vibrator works to knock any loose powder off. The pinch is closed to complete the fill and the packing head deflated. Another type of dosing method is the tubular type screw feeder. Typically less than a metre long, unless a longer transfer is required. The outlet of the main equipment, i.e. a mixer or dryer, might be too low, for instance, for a pack-off system to go underneath. By use of the screw, it can be transferred upwards to the top of the packing system. The unit comes complete with an auger, is shown here with its own motor drive, chain drive or direct drive, and can have wash in place or clean in place compatibility. Traditional screw feeder. Indeed, Hosokawa has its own unit. This is the most accurate dosing method, but it can be slow. Traditional rotary valve, shown here with the slide rails to enable the rotor to be extracted for access cleaning without scratching the bore of the valve. A dummy end plate can be fitted with a spray ball for cleaning if required. The unit can be slow on filling and only really works with free-flowing materials in the main. The oscillating valve. This particular unit turns through 180 degrees, sometimes known as a flip-flop valve. Pneumatically actuated, which is omitted in this actual photograph for clarity. Similar on face value to a rotary valve, but it does dose quicker than a rotary valve. Composite valves. This particular valve is a butterfly valve, shown here, with a small rotor in the middle. Bulk filling is via the butterfly valve with trickle feed via the rotor. You can get several different combinations. The previous split flop valve we just mentioned can also come with a small rotor in the middle of the larger rotor, so you can have bulk and trickle feed. As mentioned previously, the butterfly valve is used as the main isolation valve on a lot of systems, but it can itself be used as the dosing valve with free-flowing materials. You can see here a typical valve shown with actuator. The wafer blade that actually stops the flow of material, typically chosen with a positioner to give a positional operation against a control signal. You can see here on the installation the valve sandwiched between flanges, complete with its actuator attached. The selection process for product samplers can be very difficult. All powders have different flow characteristics, and you must always get full material characteristics and ensure you understand how the samplers are to be cleaned. This is a much older sampler, shown here, with a large pneumatic cylinder fitted, housed in a stainless steel box. Sampling systems type unit, manual or pneumatic operation in general. Cup type. It has a large diaphragm seal on the end which seals against the inside wall of the product chute. The cup rotates through 180 degrees to dispense the powder down the chute, and the powder is collected in a jar. The jar can be located inside a horizontal laminar flow booth or a glove box. Normally the jar is screw type, but it can be provided with a split wafer valve if very low OELs are involved, but this is an expensive option. The compact Sentry type unit, again manual or pneumatic operation. It can be pressure rated. It's a shuttle type unit which retracts, dragging the powder back into the unit and dispensing it down the chute to the jar. The cleaning tun dish for connection to the very bottom of the powder filling chute. As you can see here, the actual tun dish unit is actually dished on the inside. Tri-clamp freezer fitting, a manual valve for operation to release the cleaning fluid, and quick release hose connections. You can see the unit fitted here on the left hand side to the bottom of the filling chute. It can also be used to dry the system afterwards by passing warm air back up through the system. Heat sealers for various applications. We have here on the left hand side a simple non-ATEX version, and on the right hand side a very expensive ATEX rated system, sealing aluminium liners in this case. Industrial type weigh scales for back weighting the packing head and support frame onto, and IND indicators seen here, either panel mount or desktop mount for harsh environments. We have some examples on the left hand side. Back weighted frame for accuracy onto the weigh scale. In this particular case it's double height roller track to fill small or large drums, together with double height doors on the side of the actual horizontal laminar flow booth. The roller track allowing movement of drums right through the unit from one side to the other. On the right hand side is a unit inside the horizontal laminar flow booth. Top screen, again back weighted onto the weigh scale. There's a vibratory table straddling the weigh scale, with both systems originally done for pharmaceutical systems. Filling and weighing control systems. All our systems are built to customer requirements, including hazardous area and ATEX approved systems. These can be locally controlled or site-wide with DCS control, 21 CFR Part 11 capability, and then can include label printers or document printers. Here's an example showing an Allen Bradley based system with small HMI. And this is a typical mimic screen for a DCS operated system, showing a Hosokawa milling system with integrated fill waste system. Some examples of filling and weighing systems. Customized solutions. On the left hand side here we did a system with automatic doors into and out of the suite for drum entry and exit, with powered roller tracks, an inward sealer continuous liner. And on the right hand side, downflow booth application containing a pack-off system. We can also provide additional equipment to go into the downflow booth as seen here, i.e. for tipping and dispensing equipment, comb mills, sieves, etc., all prior to the pack-off unit. In the downflow booth we can provide 5-axis high containment screens complete with glove ports through which the operator can pack off. As well as the standard glass screen, shown here, we can provide flexible screens with glove ports. A system we've already seen today, installed in a minimum of time in response to the bird flu vaccine requirements. This is a simple IBC pack-off with no head height available, so we put in a tubular screw feeder used to transfer the material up and into the top of the packing head. Screw feeder can be seen here, packing head here. Drum dispensing system. This is a 3D model of the unit, shown packing off with the drums here, with the ability to pack off FIBCs as well, shown here. And here we have a very similar type unit, FIBC and drum pack-off system, but in a horizontal laminar flow booth, shown here surrounding the unit. In this particular photograph, the drum can be installed here, and this particular setup can be removed by the fork truck points, and FIBCs can be sat on the frame and hung up in the booth to be filled, complete with vibratory table with the orange motors. Another example of an FIBC and drum pack-off system is one shown here with lower doors, and on the right hand side is an older type STOT system with STOT sampler and a tubular screw feeder to actually feed the product into the packing system. Glove box pack-off examples. Note on this particular one, the cleaning ton dish again, actually fastened to the bottom of the fill waste system, with the hose going to drain. This is a fill waste system in a glove box. Drum enters and exits via the door shown here, but it has to be wiped down after filling before exit. And this is a picture of the same unit showing the fill waste system. Fill waste system with the liner loading cage removed. This was a continuous liner system. The inward sealing head, and as you can see there's the HEPA filters for the glove box inside the chamber with the HDPE dust caps. This is a drum pack-off system with Hosokawa farmer hammer mill located above it in its own glove box. This is the farmer hammer mill with the rotary valve, with the system feeding down into the packing system. And on the right hand side you can see the bottle filling facility with split wafer butterfly valve, as well as the unit being able to pack off with continuous liner into drums as well, all onto the weigh scale with roller track. Hosokawa could undertake containment testing as well, and on this particular system that I've just shown you, you can see some of the testing points here on the inside of the actual unit. This particular system achieved 0.3 microgram per meter cubed. Hosokawa always do an FAT test on all equipment, with clients actively encouraged to be present. We can also offer a full factory acceptance test utilising placebo products. Here we built the complete milling system including pack-off system, shown here, and ran with placebo over a series of trials. As you can see, we did temporary structures as well to mount all the equipment, the milling chamber and the reverse jet filter located above. Hosokawa Micron can also offer full installation or expert assistance, as well as commissioning services using our trained operatives. We also offer a full spares and after-sales service via our network of service engineers. That concludes the presentation, and I'd like to thank you for listening.
Thank you, Dave. We appreciate the presentation, and we will now start the Q&A session. If you have a question for the presenter, please feel free to submit it using the question and answer panel along the right-hand side of your screen. If we're unable to answer your question live during the presentation, Dave or another Hosokawa representative will contact you offline shortly. All right, first question. What is the achievable concentration level of oxygen with one purge of the bag liner?
Typically on that, Greg, we'd be able to achieve something like 7 to 8% oxygen content with one purge of the liner. That's what we've measured when we've actually done some testing on commissioning.
Okay. Next question. What about trapped fingers in a pneumatically operated inward sealer?
Yeah, that's a good question on the inward sealer. Obviously when they're manually operated on gas struts, they would the operator is obviously in full control of the unit. With a pneumatically operated unit, of course, he's pressing the button, but there may be some concern from site safety that people could actually have a finger between the actual inward sealer as it moves up pneumatically to the actual filling head. But we've actually shown that there's not enough force to actually trap fingers or cause any injuries on that. We've actually done some videos with some what we call the carrot tests for some particular clients where we had to show this function.
Okay, next question. What is an LEV?
The LEV, Greg, is the local exhaust vent, and normally that would be provided by the customer. And an LEV can either be from a local exhaust vent on our system, or through our HEPA unit, you can go to an LEV. And that LEV can go to a client's site-wide dust control system, or in certain instances, if it's a clean supply, it could actually go to atmosphere. But that's few and far between these days with the legislation getting ever more stringent.
Okay. Next question. What are the FDA-approved seal materials?
Normally it's silicon or EPDM.
Okay. Next question. What filling system is suggested for pharma applications where sealing height is a limitation?
In terms of it being, it depends actually on the actual process as to what we would actually put in there. But if it's and whether it needs, in terms of, you have to consider the OEL on the system, and whether you actually can use a single liner or a continuous liner, or whether you could actually use a simple downward sealer. So these things have to be taken into consideration, and the maximum height of the system with the lower room height, it has to be worked out, if you like, by an upfront system sketch to enable to see what we can actually fit in.
Okay. Next question. What is the maximum height of a liner loading cage?
Typically on the continuous liner loading cages, we would normally look to get a cage about 500 millimeters in height, which should give enough liner that when you put on liner of something like 75 to 100 micron, which is the typical for things like chemical or food applications, you can most probably get about 15, maybe 20 drums bagged off with a continuous liner. What happens though in certain instances now with the pharmaceutical industry is that they tend to prefer much thicker liners. So we're getting up to systems where it's 150 micron thick, and therefore you can't get as much liner on the actual liner loading cage. And so in terms of drum numbers, you can be down to about 8 to 10 drums on a pharmaceutical application with a 150 mil thick liner.
Okay, next question. My powder is non-free flowing and sticks to everything during discharge. What can I do?
Yes, some of the powders that we come across, again, particularly in the chemical and pharmaceutical industries, can be extremely sticky. And what we tend to do then is we tend to look at the potential solution we can use in terms of the dosing equipment, and we'll actually undertake tests at a fairly early stage with some of the dosing equipment in conjunction with maybe some suppliers of the dosing equipment that we work with quite closely, and we'll do some tests. And in particular, we had one in the last 12 months where we actually did some tests with the oscillating valve. And we actually came up with a system. It was a product that actually stuck to the inside of the chute completely and wouldn't move when you started to dose after the first drum was charged. And so with a combination of vibration, and we actually fitted a purge system on the underside of the valve. So it actually cleaned the actual pockets on the valve to ensure that they were clean and the material flowed a lot better than originally.
Okay. Next question. This is actually, I think, based on one of the first questions. The same viewer asked. He had originally asked, what is the achievable concentration level of oxygen with one purge? And he came back and said, why do you do a second purge in the operation then?
Sometimes with the second purge operation on the liners, whether they be single or continuous, is that some of them, again, as I've mentioned previously, is that some of the liners now are 125 or 150 micron thick, and occasionally they can not inflate quite properly, or they're still folded over on the first purge. So what we would actually do is actually give it a second purge operation to actually shape it fully. The other reason being, and the major one, is that the oxygen concentration for certain materials in hazardous areas, that could potentially need to be lower than can be achieved with a single purge. And so on that second purge, we'll give it a second purge, and the actual oxygen concentration level can then be lowered to something like 4 to 5%.
Okay. Next question. What is the cost of a typical filler system?
It depends what we're actually looking at. If we were looking at something like, if we can find the slide, this type of particular system, it's a pharmaceutical system. It is, although it's an outward with only an LEV, it hasn't got a horizontal laminar flow booth around it, but it is quite a sophisticated system in terms of the control package that was provided with it, and the double inlet purge valve, sampler, continuous liner. You'd be looking somewhere around about the $170,000 mark.
Okay. Next question. What is the difference? What difference do lower or full doors make in a booth system?
In terms of the horizontal laminar flow booth, I'll just find you a picture we used on this particular unit. This particular unit on the left-hand side here is shown with the lower doors, and in conjunction with a screen at the top. What we can do is two things. The booth needs make-up air from where the unit is located. So, for instance, if it's fitted in a pharmaceutical suite, you have to bring in some make-up air to allow the air to be taken away into the horizontal laminar flow booth into the extract system. And so in achieving that make-up air, there might be limitations on the HVAC, for instance, so that the actual room has only got a limited supply of make-up air through the HVAC. So in those instances, what we would do is the ½ meter a second airflow would actually only be on the aperture between the lower doors and the upper screen. So we would, as shown here, So the gap between the two, where the operator can still have access to the liner and can still tie the liner off, whether it be single or continuous liner, that would still achieve the ½ meter a second ingress of air to provide containment, secondary containment to the operator. The other system we can do is where make-up air isn't a problem, is that we can size the whole front face of the horizontal laminar flow booth for ½ meter a second. And that means that when the doors are shut and the screen is brought down, because we're extracting still the same volume as when it's fully open, the airspeed will increase on the aperture between the two, maybe up to 0.7, 0.8 of a meter a second, and we get an increased airflow protecting the operator.
Okay. Next question. Do the Hosokawa fill waste systems separate mixed powders?
Could you repeat that again, Greg, please?
Sure, no problem. Do Hosokawa filling and weighing systems separate mixed powders?
They don't separate. They wouldn't separate mixed powders. No, you would have to. I think on that particular, you're looking for a piece of process equipment maybe to separate two distinct powders or materials between the two. But a fill waste system wouldn't separate the two, if that's what the question pertains to.
Let me see if they provide more information, what they're looking for. In the meantime, next question. Would an IF filter get wet in a liquid application?
Typically in like the liquid application that I showed you for the bird flu, the horizontal, this particular unit, what we did was we removed the IF filter on this particular unit. And what we would do is on a liquid application, because the IF filter internal in the head, as we showed previously, that's a cloth material. It's like a Gore-Tex material, like a filter bag material. So we would remove that, and if we needed something in there, we would actually put in something like a metal mesh type filter.
Okay. Next question. On a compact inward sealer, do you make one that would fit a tote bag that has a 40-inch fill neck?
If I would have thought that's possible. I mean, we normally go on lay flat size, so it's most probably something that we could look at offline afterwards. But yes, I would have thought that it's achievable in terms of that. We can go up. Typically, what we've done up to now is 500-600 millimeters diameter size inward sealers. But I would say that there's no problem with going larger if need be.
Okay. Coming back to another very similar question, one asked before, the customer asked, does Hosokawa have data to prove that a filling and weighting system does not separate mixed powders? So I guess they're worried about segregation.
I suppose yes. In terms of packing off, essentially, what the question is pertaining to is, as we're actually packing off, does it separate the material? I would say that in terms of tests that customers would undertake, let's say in the pharmaceutical industry, that separation doesn't take place when we're actually packing off. But we wouldn't actually be party to that information if that's really the customer's own internal information, if you like, as to whether separation. We would only find out about it if they actually came back to us and said that was actually happening. We've not had an instance of that.
Okay. Next question. Are there any advantages of using a pre-packed liner?
In terms of using the pre-packed liners, yes. I mean, it saves the operators actually loading their own liner, and the pre-packed liner, you can most probably get more actually on the actual pre-pack than doing it yourself on the liner loading table that we showed on one of the slides. That particular unit, you can most probably get more on the pre-packed, but it is a lot more expensive. The pre-packs for operators is possibly easier to handle in terms of if you have a pre-packed liner and you put it on the standard metal cage as shown in the right-hand photograph here, This is just a pre-packed liner which is just put straight over the metal liner loading cage and then loaded to the filling head. So for ease for the operator, it's most probably a little bit easier than loading their own, but they are more expensive.
Okay. Next question. What sort of containment level can be reached with an HLFB fill-way system?
With the horizontal laminar flow booth fill-way systems, we've actually done some testing on those, and we've actually got less than 30 nanogram on the most recent test that we've actually done.
Okay. Looks like we're running a little over time here, so we're going to take one more question. If your question was not answered during the presentation, Dave or another Hosokawa representative will reach you after the presentation. So Dave, this is the last question. Don't you get material in the bearings and seals, etc., due to the powder ingress in the screw feeds?
I think what we're talking about there is on some of the dosing equipment, like the tubular screw feeder and the normal type screw feeders. These particular units, certainly for the pharmaceutical chemical industry, we actually have a purge system on them. So whether they're actually a lip seal type unit inside on the actual shaft stroke bearing construction, or whether it's actually a mechanical type seal, we can actually have a purge on that, which will actually purge and prevent any material ingress back down the shaft into the bearings themselves. And you actually get a slight purge into the actual product. So if it's a pharmaceutical, for instance, you'd have a nitrogen purge on there maybe, certainly for hazardous system. So the actual nitrogen would then the small amount of nitrogen would actually leak into the actual product and just be taken away by the extract.
Perfect. Well, thank you, Dave. We appreciate your time today in the presentation. We hope everyone enjoyed Dave's webinar and found it informative. The presentation has been recorded and will be posted to Hosokawa's websites in the next 24 hours. You will automatically receive a link to this video when it's ready. Please feel free to share this with colleagues and friends. If you have any questions, please feel free to contact us with the information shown above. Thank you so much.